discussed classical field theory, including Lagrange formula as well as Hamiltonian. We divide the equation motion for general given Lagrange by range fields. We also talked about the locality constraint for usual field theory. In the classical level, we saw basically all the fundamental field theory satisfy the locality. And in fact, locality is one of the main reasons to introduce the concept of fields. In the last part, we mainly focus on the symmetry property of classical field theory, in particular, we discussed so that theorem says that for any given continuous symmetry for a theory, there exists a conserved current. As we saw last time, both the symmetry transformation and the conserved current can be expressed in a very general form. For example, we can express the field after transformation in the decimal form associated with the small parameter alpha and some particular operation or operator acting on original fields. Then we derived the conserved current. J mu is given by two terms, basically. The first term is basically the derivative of the Lagrange with respect to the phi derivative, which is the conjugate momentum, basically. Multiply delta phi. This is the first term, and the second term is the factor J mu x, which comes from the variation of the Lagrange for this particular variation. We denote this particular variation by the hat. Yeah, so in particular, we can prove this is indeed, and we also saw there's an associated conserved charge, which is time independent. All this is a discussion at this moment is only about the classic level. So in today's course, we will see this kind of conserved charge or conserved current play also important roles at the quantum level. Yeah, so this is the content of the last lecture. Do you have any questions? So the main goal of today's lecture is going to finish the quantization of the fields. So in the last few minutes of last week's lecture, we mentioned the canonical steps of quantization. So let me continue to discuss this quantization procedure. So we summarize the steps of quantization on any given system, as a system. We have such experience coming from the context. In the first lecture, the contents are harmonic also. So we summarize what are the steps to do this. The first step is basically we should work out the equation motion and promote the equation operator equation. Second, after this, we should find the solution. Solution. So when you find the solution, you basically get the evolution equation for this operator. Okay. Equation motion. After motion, you get the operator equation. The mathematical solution for the equation motion also the solution for the operator equations. And so when you have the solution, right, you can distinguish what are the parameters, okay, and what are the operators, right? So, so we can just look at the solution. We can try to promote the only possible integration constant. In this solution, two operators. Okay. Right. So then you get the full information about how the operator works. Okay. Because in the solution, you see what are the operators, what are the other parameters, and you can see how the operators will change as time goes by. Now, this is only about the operator evolution responding to classical equation motion. Right? Of course, we didn't finish the quantization procedure. So after this, we have to impose the so-called quantization condition. So in the case of harmonic oscillators, it's basically a divariate. A condition is a divariate equals to 1. Such kind of condition will is so-called the canonical quantization condition. Of course, this condition will be imposed for those operators, which corresponding to the integration constant. Then after we get all this commutation relation for those operators, we're trying to build up the hyperspace. Just use this operators, constant operators. In 3, and we use so that's it. If you like, then after you got all the hyperspace or the space in the hyperspace, you can check all the properties for any given space in this hyperspace. It's basically done. If you can implement these 5 steps for a given field theory, then it's very, very good. Basically finish the quantization of a given field, right? Now let's do it. So now we want to do the same thing as the harmonic as what we did for harmonic oscillators, but now for the free fields. the free fields. We already know the equation motion of the free fields, right? For example, the simplest free scalar equation motion will be a box I, let's say, mass list, we have a box I, which is equals to partial t squared minus square I equals to 0. This is the equation motion, right? Right, we just really honestly follow this step. You see, first step, we should work out the equation motion, right? Just work out the equation motion. And then what we do? Try to observe the equation motion, right? Whether we can try to do something similar to harmonic oscillators. That's the idea. So look at the equation motion. The key thing, the following key things will be try to find the solution, right? Try to find the solution, right? Yeah, you may easily write down the solution to satisfy this equation motion. It's not difficult. It's not difficult. But let's do step by step. So the first observation will be one can try such kind of solution because of the space translation invariance. We know this equation motion satisfies the space translation invariance, right? If you move along x, y, or z, the equation motion does not change, right? See? So one can try, because of space translation invariance, one can try some solution looks like this. Okay? Right? Because again, this equation is only about yeah, we can just plug in this kind of ansatz into this equation motion, try to solve it, right? So if you plug in this, you will get the equation, of course, for the AT, right? Or AT. So partial t squared will get plus p vectors will act on APE will be equals to 0. Okay. Yeah, let me explain the index a little bit. Now, to brief the notation here, whenever I use a subscript index little p here, this p, this small p, okay? This p actually means p vector. But I'm lazy, I'm not trying to do something like this, I'm just escape this. But to clarify, this p means this p vector. Clearly, because this is the ansatz of my solution, okay? This p depends on p, so I put AP coefficient here. Now, if you want to just plug in this ansatz into the equation motion, you will get a constraint for this APT, right? Right? The logic is if you could solve this new equation to obtain the APT, then together with this phase factor, this factor will be the entire solution of the original equation motion, right? Right? It's something you always do, right? Indeed. So why you may ask, keep asking, why you want to represent this equation motion in this new form? One reason it's quite clear will be this equation is nothing but the energy of the equation motion of the harmonic oscillator. So the harmonic oscillator equation motion is precisely x double dot plus omega squared x equals to 0. You see? So I'm trying to do everything very closely in analog to the harmonic oscillator. Okay? You see? The double time derivative. You see? X is the analog of this APT this time. Okay? Because APT is the function NOT. Okay. For the moment, let's just forget about this p index because we already solved the p dependent part here. Okay. So just this is really the analog to each other. That's the point. So in order to identify with this equation, we can do something, redefine this part as into, just redefine this into some omega square, right? Then these two equations will be the same. See? Yeah, indeed, we can do that. So what? So yeah. Of course, you can continue just to try to solve this equation. It's not hard. You can just solve it. You will get the t dependence of APT. Okay. Then you plug in this solution back into this general form. Okay. You can general form. Then you try to write down just as the same step as when we solve these harmonic oscillators. Remember that when we solve the harmonic oscillators, we first try to find some special solutions. Okay? Then write down the most general solution. Okay? We just do the same thing here. So a general solution will be phi xt equals to, you see, here I treat this as a special solution. And you can easily check. Once you get to the APT, and together with this factor, you can easily check any linear combination of this object combine in the P space, okay, will be also a good solution. Okay? See, easily check that one. Still satisfy the equation motion. That means I can write the most general solution even as a form about the integral over the P space, and then put this special candidate or the special solution inside this integral. Okay? Inside this integral. Again, this is the solution. Now, in order to make this the really most general one and keep the reality of this field, as what we did in the harmonic oscillator case, we have to add up the conjugate piece. So we have to do the complex conjugate AP star T expression minus I. And you can easily check. Just plug back this into this equation motion. You immediately realize that this is the solution. Okay? Okay? Provided the APT satisfies this one. Okay? But then you ask me, how do you solve this one? I mean, this is the same equation as harmonic oscillator. I mean, you can solve it. Okay. Now, let me emphasize a little bit about this integral. This part, there is an important point about this measure. Okay, this integral measure is only about the three momentum space. Does not include the fourth one, which is the energy. Okay? This is only about the P, Px, Py, Pz. Okay. Okay. The reason is obvious because initially we expand the solution only in this XYZ directions. It's like Fourier expansion, right? You should be very familiar with this one. So do a Fourier expansion for X, Y, and Z, and try to find the solution. This will be the most general solution. Okay. Now, I want to make this, even though I already obtained the most general solution, I want to make the form more simple, more compact. And I realized that if you still remember, the solution for the harmonic oscillator type, the final solution will be nothing but APT. The solution for APT is nothing but some integration constant times the exponential I omega t, plus minus I omega t. Okay? Then I can further isolate this time dependence from this APT. Okay? And then I can package that time dependence into this exponential IPX and the exponential minus IPX. I can make the two factors as the exponent as the inner product of 4 vectors rather than 3 vectors. Okay? Just observe the time-dependent factor. You can easily achieve that one. Okay? That means the same general solution can be packaged or written in another beautiful form, which is, of course, this part does not change. Okay? This here maintained. Here, the 3 momentum integral. But the other part, I can put in a more compact form, which looks like AP star exponential IP of x, which might minus. First is minus. Okay. See? Again, this is similar to the general solution for harmonic oscillators. If you still remember, because we now picked up or isolated out some integration constant. Remember AP, in this case, AP and AP star will be constant. Okay? And this P and X are 4 vectors. So P dot X is the inner product of 4 vectors. 4 vectors means the vector in the coefficient space. In particular, this time P mu as a vector will be omega P vector. Okay. This is the original XYZ direction momentum, right? Now I combine them with omega. Now, as the definition of this omega, I just take the log of this P. Okay, with this one. Okay. A few things you have to note, pay attention. This omega is not independent of this P. Okay, this is very important, right? Otherwise, that integral is a little bit sick, right? If omega is independent, then this integral will be dependent on omega eventually, right? It's a little bit sick if you haven't integrated over omega. Sorry? Why? Okay. Yeah, we will see why. It will be very convenient. And of course, you can express it in some other forms. Yeah, the reason is just coming from we just take use of these translation invariants. We want to decompose a field phi in this special momentum space, but not yet t direction. Not yet t. Well, you can equivalently express say, okay, I don't like this transform. I like the do the Fourier transformation or Fourier decomposition for the entire full space, including time. Or you can do that, but remember that if you want to impose the equation of motion, then there will be an on-share condition, right? The equation of motion is equivalent to in momentum space you impose some other constraint between p squared and m squared, right? Then you have one more constraint. Then, in order to make this integral clear, if you express it as the 4-dimensional integral, you have to insert a third function. Is that clear? But I don't want to use that. I want to take use of this one. because now everything is clear already. Okay, we know this is three P1, P2, P3 are independent. I take them integrate, and the other one is not independent. Yeah, I just bring that together in this expression. That will be enough. Right? Now again, analog to the harmonic oscillator, the only different point that you should see, okay, in the case of harmonic oscillator, we don't have this one. Okay, remember that? And then we indeed have such kind of structure, but this exponential will be only about the time dependence or time evolution in the case of harmonic oscillator. Now, the additional structure in this form, okay, to express a field, compared with harmonic oscillators, we indeed have more space, P space, and there we have P independent piece here, okay? P independent piece here. Okay? But it's okay, right? You can just fix P to see, okay, this is nothing but harmonic oscillator. Is that clear? Now, since all the different P, for each P, you have a good solution for your equation motion. So the most general one will be take the linear compilation for all the different P, right? Which is essentially to take this integral. Clear? Now we obtain the most general form. Now what is the next step? We finished up to where? Up to here, right? So it's already finished. Now we're going to step 3. So in step 3, what should we do? We should just put hat as a harmonic oscillator. Let's put hat. Put hat. Okay. Now, as before, we should put AP hat here, and we should erase the star and change it to dagger and put a hat once again. Clear? Indeed, we do the same thing, precisely the same thing here. Okay. Now, only one small change in order for, it's actually not a big deal, but for convenience. Okay. Now let's try to make some observation. Now, since this is a 4-vector inner product, as we already learned before, this kind of thing, the Lorentz index will be contracted over. So this part will be Lorentz invariant. You see, this part will be also Lorentz invariant. At this moment, we don't really touch the property of this A hat and A dagger hat. We will postpone it a little bit later, but just look at this part, right? Because these are the easy structures, right? This one, including this one, are the easy structures because they are not operators. They're just functions or numbers, okay, or parameters if you want. Now, I want to make all other structures to maintain Lorentz invariance. So I will promote this integrate measure into a new form. And this omega is this omega. Okay. Or sometimes we denote it omega p, but just for it's the same thing. Okay. Because omega is not independent as such.
Is this p will be also better or just some other?
No, it's the form momentum in Minkowski space.
So the E omega should have the exact form of because it's using the special relativity.
No, the point is this momentum the any for like it depends on the particle. If your particle carry this small momentum, the larger one, we just get different. Depending on your velocity. Yes. Any other question? Right? That's clear, right? But the on-share condition is always true. On-share condition is okay. Let me write. This is enough, right? This equation will be enough, right? But this is on-share condition. So whenever you increase p, you're getting a larger omega, right? You see, this is massless. This is massless particle. Now, if you have a larger special momentum, you get larger energy. That's it. But p can change, of course. Yeah, this is a little a small insertion of this new factor. It's quite related with the previous question. We don't yet right now write everything in the full momentum integral or Fourier transformation or decomposition pattern. So in order to see, I still maintain this three-dimensional integral in p space in order to maintain in Lorentz environments a little bit promotion. But this is okay, right? This is just some function number coefficient. It doesn't matter really matter for the operator properties. Yeah, that's a small comment. Now, what else? Nothing else, right? We basically we're done. Now, just accept AP hat and AP hat diagram operators. It's finished. Now, step 3. We finished step 3. Now we are going to the step 4. Step 4 is about to impose quantization condition. Now, before that, let's emphasize a little bit. Really try to understand this structure. Means observation. Okay, because now we are going to impose the quantization condition. Quantization condition is not something you can easily derive. It's a condition you have to impose. It's not something you okay, I can derive it. It's not. So you have to make the correct choice. What are the correct quantization conditions? So how to make the correct choice? Do observation. So the observation here is each p vector is a simple harmonical oscillator. We already saw here, right? As said, for each p means forget about this one. Okay, this is the sum over the p space. Take p as some fixed value. Okay. Since it's a fixed value, then the p dependent part, these two factors will be fixed. Now the time dependent part will be like exponential I minus I omega t, and here is exponential I omega t. Okay. So this is nothing but a harmonic oscillator. So for each p, there is a harmonic oscillator. So then, since this is the fact, so we just treat AP. One can treat AP and AP dagger as the annihilation operator and the creation operator for each p, just as the usual case in the harmonic oscillator, as the annihilation and the creation operator. With the quantization condition, as the form, we just try to inspire from the harmonic oscillator. Let's write the harmonic oscillator form. In the case of harmonic oscillator, we get a commutator with a dagger in 1. Now, we want to promote this one to be we treat it for each given P, for each P, different P, we have such kind of structure. Okay? Then you have to just basically add an index into this formula, right? Just add an index. Okay? So what are those? This will be, let's say, AK. Let me first write down and try to explain, check. Consistency. Yeah, this will be the analog of the a dagger computation relation in this momentum space. We already saw for each P, different P with harmonic oscillator. Now the only thing we need to do is just try to make it in a more general form. The general form is looks like this. Say for different momentum, say if K and P are different, this is 0. Okay? This is 0. Means what? Means there is a simple harmonic oscillator staying on each different mode for different momentum. Okay? Just think about it. Immediately think about that. A fixed momentum, some kind of mode. The fixed momentum mode looks like some plane wave. Okay? Intuitive picture. Now think about it. This kind of mode can carry different momentum. Okay? The point is, for each momentum, you have a harmonic oscillator. You carry the harmonic oscillator. Now, for different momentum, for the modes with different momentum, we don't think that they touch with each other. So that's why for different K and P, there's no non-trivial commutator. Something like 1, you just get 0, right? So the right-hand side is non-trivial, only happens when K equals to P. Clear? This means the non-trivial commutation relation happens only for the same mode, carry the fixed momentum. They don't cross. They don't cross each other. For different K and P, that's non-trivial commutation. Does not happen. It just happens in this very stupid way. Now, then you ask me why there's a delta function. Well, you see, this is a continuous space. We're now working on making everything in the continuum P space. We're trying to identify the right-hand something analog to the identity 1 in this continuous space. The natural choice will be the delta function. And these 2 pi to infinity factor is some normalization factor. For convenience, it doesn't really matter. So this will be the correct canonical quantization condition. And as before, we have some other trivial commutators. Let's say if A take a commutator for AA, whatever KP takes as well for A dagger, whatever KP is will be always 0. Simple enough? Yeah, that's the step 4. Step 4, we have to impose. We have to impose quantization conditions. Now it's yeah, but you might often see some textbook, for instance, express this kind of quantization condition in some different form, but there will be just the equivalent. For instance, from this kind of commutation relation, you need to check. This will be equivalent. So some other form, for instance, now we know now all these phi we promoted already being 2 operators, right? There's no more classical field. Now phi is operators. You can also talk about the commutators about phi. For instance, you can try to work out the equal time commutators between phi and phi. Right? Because now you already have, you almost have everything ready to check this commutator, right? If you know what is phi hat, what is phi hat, just plug in that formula. Phi hat is only about some combinations of a diagram. Okay? Just plug in through here, you check it. Check. If you take use of this a diagram commutation relation, you can check this one, this kind of commutator. Also some other type of contribute pi. We know pi is nothing but phi dot. So we also know pi. Okay? So you can check both these two at equal time. At equal time, this will be equal to 0. This is basically the analog of this second line, these two commutator equals to 0. Okay? I shouldn't say analog, coming from there. Now, the only non-trivial commutation relation in terms of phi and pi will be this one equal to I delta x minus y. Okay? So you can easily check these three conditions is equivalent to these three conditions. In what sense? In the sense that you take use of this expression about the relation between phi hat and a diagram. Either you impose this one, you can derive this, or you impose this one, you can derive this. Okay? So in that sense, they are just equivalent in different form. Right? So what is pi? We already learned what is pi last week, right? Now just to promote everything to operators. And that's pretty straightforward. Now we can make a mark here to finish again step 4. So the last step is to try to build up the hyperspace. So now we are arriving at step 5 to build up the hyperspace. Again, as what we did for harmonic oscillators, we act AP dagger, okay? We act AP dagger on vacuum. Of course, you have to first define your vacuum. Vacuum was defined by the state carried by all the A, for all the P, okay? AP, okay? Because P can change. P is the index. So your vacuum has to satisfy, it to be carried by all the AP for different P. That's my vacuum state. Once you have that vacuum state, I can try to act the AP dagger on the vacuum state to generate a non-trivial state. That's the idea. So vacuum is defined to be AP act on it will be always 0 for any P. that clear? So it's basically just treat the p different p as the index. Okay, we just take them separately because they don't touch each other as so from the computation relations, right? Now you get the entire Hilbert space, which consists of all the different little n small space. Okay, little n means how many times you act on the vacuum by a diagram. Okay, doesn't matter you use the same p or different p. Okay, we all count as the little n times the little n. Okay, so basically little n is the number of the particles. Because okay, yeah, let me first write down this and explain. Try to give the explanation or interpretation. For instance, I can take all the P1 to Pn, P1 to Pn, P1 to Pn can be the same, some of them be the same or other are different, it doesn't matter, whatever momentum. Okay? Because P is just the index. You can choose whatever you want. So I can act, the point is I act n times. Right? I act n times on this vacuum. And this is the, I take into account all the possible p's. N times, all the possible, including the same or different p's. I put all these possible states into this H with a small n. Okay? And I also allow you can change your little n. The n can be all the possible positive integers. So all this subspace put together form the entire Hilbert space H. Right? So mathematically, this is quite clear, right? Yeah, the structure is quite clear. Right? You have some correlation operators. The correlation operators carry some non-trivial index. Those index might be continuous parameter. That's fine. I can just keep acting on the given well-defined ground state. Then I can form an entire Hilbert space. That's it. It depends. You can somehow classify your space in different categories. It's okay. The space in that space. You can say I count. Yeah, I try to look at the n particle space, or I try to look at something else. That's fine. That's how to divide your space. That's fine. So this is the final Hilbert space. Sometimes we call this the focus space. So now let me try to focus on the interpretation, physics interpretation. So far, all about the algebra structure. So what are the correct physical interpretations? That might be an important question. So we said, already mentioned, we want to interpret this as an n particle sector. Which means that there is an important point here, which means that now we interpreted a P Geiger acting on a ground state. This is a create one particle. Create a particle. One particle. Yeah, this is something important. Why? Because this is totally different from quantum mechanics. You see, this is different from what if you want to. I said at some point QFT is quite similar to QM. You should always go back and try to understand. But this is something different. Okay, this is something different. Remember, in your harmonic oscillator quantization, if you keep act a dagger on your ground state or vacuum, you just treat, okay, I get more energy or frequency mode, right? You don't think you get some new particles or more particles. You don't think in that way, okay? Because the entire system is one particle or some fixed number of particles. Particle number does not change in that case in quantum mechanics. But in this case, we give a clear interpretation about this kind of thing. We just think if you do such kind of thing, act on your vacuum, this is creating a particle. Which kind of particle? Of course, the particle will carry the momentum p, right? Will carry the momentum p and the energy omega. That's your particle, right? Yeah, this is the interpretation in quantum field theory, which is different from quantum mechanics. Yeah, so this is something important. We were saying, okay, you may keep asking, say, why you believe such kind of interpretation is correct, right? So we will keep providing more evidence to support such kind of interpretation as we will see continuously. Indeed, the correct way to interpret such kind of state is one part of the state. Means what? Means if you're doing more, if you're doing such kind of thing, create some state look like this. This is a n particle state. The n particle all carry different momentum, p1 to pn. Okay? The system is such kind of system, or the state is describing such kind of n particle system. Okay. So I actually skipped some calculation details, but usually escape. This is very important. I thought you can straightforwardly check. Divide this from here, divide this from the university. Yeah, it's really worth to perform these calculations. So maybe we can, we can try to sketch the derivations for this equal times coordinates. For this one, or third material communication relations. Yes. Yeah, the key point is always take use of this expression. So maybe this is the most, this is one of the most important results in today's course. Remember, always remember this. Okay. In the free field chapter, this is again one of the most important formulas. Okay. So you should, you can almost take this right hand side as the operator definition of that left. See, right? Because you already assign all the operator meaning into this A diagram, A hat and A hat diagram. Or other parts is like is trivial, right? So only, in other words, only these two pieces are the operators. So all other parts is about the trivial evolution or piece-based decomposition. Right? The reason is just because your field, your continuous field, is so complicated. It's not some discrete simple harmonic oscillator system. It's more complicated. It's like infinite harmonic oscillator. We have to using some integral or decomposition or Fourier transform, whatever we want to express that phi. Okay, but in the operator point of view, right hand side is really the definition of phi hat. Okay, just writing phi hat doesn't mean much, right? You don't have any message or how to understand this one. But right hand side give you a very good way to understand it. So you can take a right hand side, the operator definition on the left. Now, if you have this one, we also have the commutation relation between these two. Then basically you can work out many other relations. You basically know how to deal with phi as an operator. Anywhere. Yeah, that's the point. For example, you can just plug this in to check this commutator. Yeah, because now we finished this one. Sketch the list we implement all these different steps. And easy. So we basically finished the procedure how to quantize a field of three fields. And now let's do some consistent check why that kind of thing makes sense. Okay. For instance, first thing you can check is how to calculate this commutator. So at phi, I know the commutator diagrams. That's enough. Let's do equal time. So after you can do it, right? You see, just plug in that expression. Okay. If you don't have operator, all the commutation will be 0, right? Because we know numbers, they are commuted. Okay. Functions, they are also very often they are also commuted if there are no some non-trivial differential operators. Anyway, such kind of thing is simple enough to check. And then eventually plug in this A in A diagram commutation relation, which results in some delta functions in P space. Okay. So if there is a delta function insertion in this P space integral, you can reduce the integral, right? You have double integral with a delta function insertion. Eventually, you have a single integral, right? Right. So this commutation relation after a few minutes, just honestly calculate. Okay. Even though we have the time dependence, this is T here, bring the time dependence here. But in the commutators, you usually find the T dependence cancel. The T dependence cancel. Okay. Yeah, you can easily check. Then eventually you arrive at this point. So what is the value of this input? What is the value of this one? No, it's not. Well, yeah, it's not. Another answer. What is the value of this one? Yeah, remember omega p here is defined as long O p vector. So what is the value of this one? So this is 0. Why? Why this is 0?
So the first part is the same as
Yes, that's right. So if you think about it carefully, this is the entire p-space integral. Okay. It's the entire p-space integral. See? And this part, including this part, if you flip p to minus p, meaning if you flip your direction of your momentum, okay? Right? The story is about to do the entire p-space integral for some object here. Okay. Okay? Then you can choose the different variable as what you want. Right? I can choose the variable, let's say p. I can also choose minus p. It doesn't matter. Because eventually you integrate over everywhere. in the P space. P space. Okay? Point is this particular integral, you can switch P to minus P. Does not change value. See? Okay? If you want to change some function, and P, now justify yourself. You switch P to minus P, the integral doesn't change. So the first term and the second term is equal. Then it goes to 0. Now about the other, you can do the same thing for the other one. I can check the phi equal time commutators, for instance. I can plug in this phi and what happens for pi. So my pi will be the time derivative of the field phi, right? And what is that? So my phi field, pi is defined as the partial t phi hat, which is nothing but minus I here minus I into P. Yeah, you just take the derivative, right? Take the derivative. Minus AP. So sometimes I just escape this hat. Now we always talk about that without the confusion. Yeah, this is my pi. This is my pi. Find that partial t phi, then plug it into this one. And again, use the only possible term left over is out of this commutation relation is coming from the A and A dagger commutator. All others is gone. Okay? Instead, A commutator equals 0, A dagger equals 0. All other simple parameters commutator equals 0. The only term, zero term left over is coming from A and A dagger commutator. And eventually, you will be able to achieve the expression I over 2, the P, 3P, with some bracket plus extension minus I, P. Okay. Previously we have minus, now we have plus. You see? We have plus. So again, so what is the value of this one? This time. Yes? Now this time is direct function, right? This is the definition of the direct function. You should know, right? You should know. In this course, we will continually use many functions like Fourier transformation. And direct function, we should know that. So this is a P integral with this part, then we get a direct function. And this one, as said, even though this minus P doesn't matter, we also get a direct function. So this we get a twice direct function, cancel with this factor 2. Cancel with this factor 2, eventually we will get this will equal to I direct function in the XY space. Okay. It's a 3-dimensional direct function. And which has not been here. Sorry, I remember why. Yeah, so we got that commutation relation between phi and pi. And we saw that indeed it's equivalent to the commutation relation between A and A dagger. Yeah, you can do something more. For example, the point is we have an elementary expression or operator definition for this phi hat. All other quantities, which you know the precise expression in terms of phi, Now you can treat them, all of them, as some new operators. Okay, defined by this kind of A and A diagram. That clear? Because phi already is well defined. Now, if your quantity, like for instance, Hamiltonian, momentum, or whatever, or conjugate variables like pi, all of them, if you can express it in terms of phi, now you can get a well-defined operator definition, right? From the right-hand side. Now we know everything about the right-hand side. That's the point. So you can use the commutation relation between the phi and the phi diagram, work out every properties of any known operators in terms of phi. So you can work out everything. We are going to continue to focus on some interesting properties for this free field system. But before that, let me give a small remark. Is this works equally well if I have a massive field. For example, then the omega p will be equals to p vector square plus m square. Okay? This is the classical relation from the standard relativity, right? Just the energy square equals to p square plus m square. Okay? Now this is with a mass, and everything everywhere works fine. Okay, just add a mass term. It's against the free fields. You can do everything. For instance, all other decompositions or operator definition are fine. Now, provided this new definition for omega p, which depends on n. Right. In this case, the equation of motion is a little bit changed. This is for massive theory. So another important, we mentioned we can work out all the operators have a concrete expression in terms of phi. The important one, of course, one of them is the important one will be the Hamiltonian itself. Okay. So what about Hamiltonian? Because we know Hamiltonian has an important physical medium, which is energy, right? So what happened for Hamiltonian? We spent a lot of time last week to work out this H, right? Work out this H from stress tensor, for example. We treat the stress tensor as a conserved current from symmetry, translation symmetry. In that case, we give a symmetry perspective or definition for the Hamiltonian. But anyway, we get a very consistent result. For instance, compare with the Hamiltonian formalism definition for Hamiltonian, you see, coming from Legendre transformation of Lagrangian, everything is consistent. So the result will be the Hamiltonian density will be looks like half pi squared plus half yeah, so this is the result for the Hamiltonian density. Okay. Again, pi is the partial t phi. Keep in mind, pi is partial t phi. But as said, in the Hamiltonian formalism, we treat pi and phi are independent variables for this curly h. H is a function of pi and phi. Now, from right hand side, we know clearly the concrete, again, the concrete expression in terms of phi, right? The three terms. You also know that the operator definition, or a Liger definition for phi. Okay? Just plug in here. Now I just escape the hat. From now on, in quantum field theory, we always treat field as operators without confusing. Just throw away the hat. Now, Therefore, one can express clearly the Hamiltonian in terms of A and A dagger. In terms of AP and the AP dagger, right? It's very straightforward. You can do it right now, right? Just plug in that formula into this one. So what is the result? Result will be yeah, this is a non-trivial calculation. You should do yourself. It's not something like that you can observe. The result will be a P space integral, again, with omega P, with a bracket. Inside the bracket, there will be a AP dagger, AP. Basically half of A dagger A and A dagger. But let me reorganize a little bit. I want to express this in terms of commutators. Then I get such expression. Okay? This will be my H. You can easily check yourself. This is the result. Just plug in the phi expression phi into this formula. So indeed, I get, we know what is the omega p, it's the trivial. Now we express the H operator in terms of A dagger and A. You see here. Even though they carry the P index, eventually we integrate over P. Right, that's reasonable, right? Basically, this says that, well, almost you can guess this result if you understand this system very well. It basically just says that in P space, let's think about everything in P space, okay? This says that if you want to count in the energy, since you already told me the system is nothing but all the separated harmonic oscillators carry different momentum, put them together without any interaction, touch, whatever, right? Then the counting energy, which means I just need to count in the energy for each harmonic oscillator. That's enough, okay? Because there's no potential energy between the two, because they don't touch each other, okay? So that's indeed, this is the result. So if you're counting for each mode, the energy, and they add up together, you get this result, right? Almost, you can almost already guess. You see, let me try to explain term by term. You see, this is about the elementary part of the energy or frequency, omega p, right, for each p. And this is the, in the harmonic oscillator language, this is the analog of the number operator. You see, A dagger and A, right? And this is the commutator, right? Commutator is, you also know that, like commutator, right? Some constant piece, basically. And this is basically the structure. The constant piece is the contributes boundary energy. But anyway, now we want to be very precise. We want to focus on this quantum field theory system. We want to study further this kind of H, because the H has a definite meaning of energy. Now we want to go further. The first thing we want to study is the second term, this term. So what is the result of this commutator? We just write down the commutation relation. So what about the AP? Commute with the AP dagger. What is that? It should be included here, right? You see? Now it's about to set P equals to K. There. What happens if P equals to K? What happens for P equals to K? It's just a delta 0. Okay? Right? What is delta 0? What is delta 0? Can anyone tell me? Sorry? Infinitely large, correct. But what about the other answers? I want to see some, what is physics quantity related to delta zero? You can easily observe. Think 10 seconds. It's already here, right? We just claimed that these two terms give two deltas, you see? Right? So this is the integral expression of delta function. Now you want to seek for where is delta zero, which is equivalent to say I said. Is this good enough to express this one? It's not. Okay, it's obvious anyway. Because here the delta function is in the momentum space. Okay, that delta function is in the coordinate space, but it doesn't matter, right? The mathematical expression, integral expression for delta function, doesn't matter you are working on momentum space or coordinate space, right? Yes.
I just don't plug delta function into its integral to get income.
Delta function, yeah, you can do that. Yes, you can do that. But I want to give you a more sharp way to understand the meaning of it. Okay. The meaning is that in the momentum space, their function, if you set the variable equals to 0, this is nothing but a space-time volume. Clear? Clear? Yes. Can you explain why? Yeah, we lower down for it, so with an equal volume, that's okay. Yeah. The point is, I can re-express, just similar to that one, re-express this delta function in terms of the coordinate space integral. Okay? Coordinate space integral. And the exponential I t plotted with x. Okay? Okay? Now I want to, this is what? This is about delta p, right? This is about delta p. This gives delta p, right? Clear? Now I want to set this p equals to 0, which is equal to set this equals to 0, right? So when you set the p equals to 0, this becomes the identity. See? Then you integrate a identity basically of 3 volume. What do we get? Get your volume. We get your volume. So this is V, okay? So for that reason, I can rewrite my Hamiltonian in terms of with the first term, but we now understood the second term is nothing but the volume times omega p, of course. Yeah, this is the result. That's fine. But as some of you mentioned, this is about the infinity, right? That's some other important observation. This is an infinite number, which means what? Which means what? Now, before that, let me try to separate this energy. This is a total energy, right? This is a total energy. Now, quite often, we don't really observe. For instance, we do experiment in the lab. We don't really observe this amount of energy. Okay. Quite often we observe something else. Whenever we talk about energy, quite often we compare with some references. Okay. We're about to measure the different energy, meaning that the energy compared with some other thing, we treat the some other thing with carry 0 energy. That's the point. Right? It's kind of relative amount of the energy. Now, yeah. So keep that in mind. It means that if you want to try to measure the energy here, for instance, I can try to separate out the ground state energy, because now I know how to give the operator meaning of my total Hamiltonian, then I can measure this Hamiltonian operator in the ground state. Okay? By definition, this is the ground state is the energy state, right? This is the ground state energy, right? That object, this is the first physical quantity by definition, has a very sharp window, is the ground state energy. Or vacuum energy, right? This is the vacuum energy. Now, quite often, we're not really talk about the vacuum energy itself, meaning that because energy is something, is extensive quantity, okay? It depends on the volume. If you have a bigger volume in general, your energy will be bigger. That's very reasonable. So it's not quite good to look at the energy itself. We try to look at the energy density, okay? So you use this formula, plug in this definition, operator definition of this H, you realize that this A term will not contribute to the vacuum energy, right? Really, because A killed the vacuum, right? You get 0, right? First term. Only the second term contribute. Now, we also know the second term is nothing but V over 2. Now, why don't you just measure something called energy density, which divided this quantity by volume? This will be a good, the good observer, right? This is the vacuum energy density. Yeah, that's good. The vacuum energy density by this observation will be eventually just equal to this integral simply omega p over 2. See, we divide the weight. Only thing left is the omega over 2. Okay, so this is my vacuum energy density. Yeah? Some very interesting physical observer. We can extract very very concrete way from field theory, right? Now, what is the value of this integral? Who can tell me? What is the value? 0? No. What? Yeah. Then what is it? Doing integral is one of the main ability in theoretical physics. What is the value of that integral? Any answer? Guess. That's right. It's infinite, of course, right? It's infinite. It's infinite. Come on, it's infinite. You just counted the powers. You didn't get a final number. Not with that integral. So it's infinite. Why is it infinite? Because this is nothing but the dp three-dimensional integral square root this one plus m squared, okay? And over 2, okay? Counting powers, you realize that this entire integral diverges, okay? Diverges. It's not converged. So this will be equal to infinity. Okay? This will be equal to infinity. So how to understand this infinity? This infinity basically indicates that the system, the field theory system, really includes infinite degrees of freedom. Okay? Because what you already learned from simple harmonic oscillators, in that case you don't get infinity. Remember that? Now you get an infinity. But these two quantities are so close, they're just analog. Now you realize that, okay, even I stay simply in the ground state, if I try to measure energy density, I will get infinity. Okay? This meaning that really everywhere in the field theory, there's infinite amount of harmonic oscillators there. Okay? If that not happen, you cannot get infinity, right? That's the physical indication about this infinity. Okay? And there are more interesting perspectives to discuss the ground state energy. For instance, you can talk about something called cosmic energy, but we don't want to go in that way. Just yeah. So now, since you already separated out the ground state energy, the lateral way to define the relative energy compared with the ground state, okay, is just by throw away the second term. You see, I just mentioned quite often, for instance, in the classical world, we don't really care about the ground state energy, right? We only care about compare with some reference state. What is my energy? In that sense, I can always just simply pick my lowest energy state that has the zero energy, right? I measure the relative energy for all the others exciting ones. That's enough. So in that sense, one can define the energy above the ground state. One can define the energy above the ground state. What is that? Let's simply throw away this second term. Or is that only the second term basically characterizes the ground state energy? Now we treat it as zero, so it means throw it away, right? So this is some h, which is actually a little bit different from this h, but we don't distinguish quite in the h parameters. This will be the EP, this one, or the P, A, P diagram. Yeah, sometimes we use this as my new definition of the energy away from or above the ground state. Yeah, this is the new energy operator. Yeah, but depends the goal. You can use either H or H prime. Depends. But the meaning of them, both of them, is quite clear. Yeah, I think it's a good time to have a break. Let's have a break.
我没法提有一个不同的解决办法，因为如果它是四个样的话，有一个开始一些然后如果你取同样情况，它不是1的话，然后它上面那个一定是零质量的场。这个一定是有质量，是更好的解决办法。
是一样的呀，因为就是第一个更多的是零和量，但是如果是这样分解，它就是相当于隐含一个这样的。亚历山大就是我刚才说了，这个欧米伽换成0.9，应该包含了这个导超量。重要的是这里怎么确定？right， 这还没讲严格的证明，严格的证明，因为 quickly sketch solution， 肯定应该保持它 real， 一定要有这个证，这证不跟 real check 就知道，这个 conjugate， 没去用左边是 real， 这个可能是 real。
这是我们在做这个说法的时候没有用到这个非常强的 real 的这个条件，但是这个是。
No, conjugate coming from 要求它是 real， 因为这样的 expression， 这样的 expression 是 real， 而且它又是解。那么更严格的说，你要证明这个，好像你有次问过这个问题，肯定是有严格证明。证明就是说，用你扔掉这一部分，它不是它的总类。对，因为比如说你错误是10个解， 如果就用这个，就用这样一个 sector 吧，让 A 来一个，对吧？这个就很简单，就跟通常的展开一样，用正弦和余弦。我们要求是两个 sector， 一个 cosine 一个 sin， 那你挨着写成一个这样正平。但你不能只写一个，只写一个，你得到一个 weird 的方式。
这个好像是不太一样啊，这个算是一个模型算非列范的这个好像是算这个
在 P 空间是的 ，T 就不一样。
在 P 空间算
T slightly P 空间可能是。
这个 P 是一个定量对。
你可以认为是个参数。P 没有正比。
对，如果那边换的话，是不是这个只有一点？就是这个负担这个影响。
Yeah, again, that 就是数学上是这样，但是 the point is 那一边就没有 sharp either A 和 A dagger， 因为 A 和 A dagger try to analog harmonic oscillator，A 和 A dagger 分别出现在正负和低大小，你要 consider 两个，就是如果你那样的话，数学变化。就你要类比，一定有一个正负前进性才能解决。因为我们这个是 justify， 我们这个只是道理，是不是要可证？是吧？
这个方式就是这个科林根方式，也是不是可以完全用那个用量法来解？
Yeah, doesn't matter 用什么方法。
对，但是如果非常好的话，就我在想的是，这边在这里非常好的话，那个系数当然就有个计算的求，我们考虑有限区。对，是不是因为是这个？
啊，你要考虑有限区，那是 different thing， 这没有限区。
这个是不是因为我们的场是无穷大定义的规定才是
？Right， 有限的话就求回了。
对，就是应该是就是在做模型的时候，我应该是考虑这个限制。考虑这个限制的时候，我们要改变这个模型的格式，因为考虑翻译模型的话，这个 phi 是不是这个变？
phi 是变成什么？
就是有些它的长的 phi 这个值变成球不是
That's possible, right？ 因为这个 consistent。如果你不让 p 然后我让 t variable， 很难叠加出一个 smooth x， 可能是取4个。日本的也可以。
但如果是这个话，那是不是不需要这个参数这个翻译过来？
Yeah， 应该有影响。
所以这个算是某种意义上是位置空间的还是影响。
位置空间。对，它itself是产生因为像。
那么我们那个按扣有这个出来做这变化，那得到的这个是产生的沿上的位置中的沿上。
啊，我们会讲，phi 生成什么态？
然后加入一个常数。这个原上不是常数，所以这两个积分是不是不等？对，做一个。
要当然不等，它
对，
它只能用 p。
对，这个是
就我要把它做成一个引导的。
对，所以这个实际上不是不变的。
就这不是从它推出来，是提升要求要写的这个形式，哪一个是能？
就是这个没有
Apart from A 和 A diagram，which 我们接下来讨论其他的事。
对，这个就可能也要变成一个因子，然后就这个，就是如果 A 变成因子，也让它正好变成这个
no， 这个 a priori 呢没有相等关系，因为可以这样理解，就是你上面就是 nothing but 一个分解，在空气空间的分解，这么问题。然后你按下面这个分解也没问题啊，你 check 是分解，为什么会分解？只不过测度，然后测度也没问题。你只要承认这一点是吧？这没问题，因为 P。AP 这个 check，P 的分解，就是这个，这是一个。第二个就是这个只是为了 convenient，convenient 什么意思呢？我现在除了 A 和 A 打一个之外，其他都不是 operator， 我最好让它是人子变，因为它不会带来 additional transformation， 就是同变。那我说白了，那我要 seek for five heads 的变化性质。只用看 A 打一个为了方便，否则你其他地方如果不是我们这样，还要分 share。另外不是 operator 的结构，它就很麻烦。
这里当然是四面结构。
No, this is the wrong result。如果你写成4个，里面不要 T， 是吗？我没有写过T，别人写的。没有 T。它只是个 constant。T independent。
这个是前面我加起来这里有一批，
刚才强调就是每一个 P 就是一个结论子，代表我们也会讲，但是它为什么是 harmonic oscillator？ 因为 harmonic oscillator 就是time double 时间导致的，加上一个欧米伽平方。你现在就是 P 按照 P， 按照欧米伽平方定义成 P 平，你得到一个严格的 harmonic oscillator 功能方程。但是就是这个意思。each P， 你 change P， 就相当于你在 harmonic oscillator 里 change 到一台。今年频率，这就是 harmonic oscillator。
但是应该是 APT 是然后 APT 作用到
是一样的呀，因为你 solve 出来，没有 solve 出来就发现 APT 是3层的 AP， 就是 constant 是 minus I， 就是它对时间依赖的 harmonic oscillator。这个但我想为了在这儿保持我们这个空间的话，空间一起去，这就是成了常数。还是不能变成造成，就你已经解出来的时间依赖性。关键我们要处理的时间也是好的，在放时间中的答案没有适当。
那我们说这个效果空间团队研究这些小效应公式这个就是我们觉得说是3粒子的这个效果空间图，还是一个1粒子和一个2粒子效果空间这个？
可以啊，就是写出来了。那你的这个问题是什么？再说一遍。
一个，比如说 H3， 我们区分 H3 和 H1 和 H2。这两个效果空间有一个 H3， 一个 H1。
当然可以啊，直合，对，不是请看一下。就是我是直接把这样的派拼在那是一个 element， 空间的 element 组合在上，就是这个派到底是3个，跟2个粒子和1个粒子组合起来显然不一样，没有缠，让你把这个概念搞清楚。这一派就是直接拼起来，是吧？作为这个空间的一个元素，这个集合里面用来做操作。 我没有把一例子、二例子再组成三例子，这能理解吗？这真的两个都是独立态，好的态。现在只是我空间里既包含两例子态，也包含三例子态，就是也包含了一例子态，显然不等价的空间里包含三例子态。就是这个态到底有几个例子 error？ 你讲完。这个应该好理解。是吧？
这从这个变动的所有已经在这个长的流域，说能量是形成能量。
啊，我这个和我现在老师就是解释这个事情，就是能量就是它们能量的本质。
对，但是就是在长的流域本身就是观测结果。
这个地方它没有跟观测有关系，至少有个实验。这个能量不需要，能量就是 so elementary 的概念，可以直接在他们中学上。光是知道能量是吧？概念当它基本到你完全不怀疑它的时候，你没有必要用观测去 justify 像能量这个东西，因为能量就是实际上中文的 general 全称。
像今年一样，或者是一样，也可以被观测到，还有一个抽象概念。
啊，我没有讲，可能是 partially 就是 cosmic energy 就是在把这个系统改一改，做成有限系统，然后把再那个再看那个就可以，这是测出来。
地方含顿量来。
对呀，就这样算出来。我就再做几个。原本的，我们这里没有区分。对啊，我们这里没有区分。原本的 Hilbert 是哪一个 harmonic oscillator 还是哪个？还常论的？我们一般认为常论 Hilbert 就是 focus， 不区分。但非常数学的那个意义，再界定也哪就是 countable， 哪就是 countless， 这可数。对，我们认为这个可以看到 include all the possible parts， 可以去望子可以生成非常大因子数，整个中间有构成的。就是我说到right， 区分常论的，因为通常认为常论的 Hilbert 才是 Okay, let's continue. So we talked about how to define the Hamiltonian operator. One interesting you can check. Over there, we check the commutators between phi is commutator partner. One can also try to check the commutator for Hamiltonian and phi. Okay? So what is the commutator between H and phi? Before we calculate it, we should go down here. H coming to phi. Did you see it somewhere? It's including the Heisenberg equation. Okay. We learned Heisenberg equation. What did you learn? We learned the H, the operator commutator with H should be given by the minus I factor T. Okay. It's equivalent to the fact that I T derivative. right? For the operator. That's the Heisenberg equation. Now we just want to justify in this point of view, because now we have something very fundamental. We want to justify everything. So we have a definition of H as an operator. We also have the quantization condition. We should be able to derive everything, including the commutator for H and phi. Now, for this purpose, it doesn't matter you use the ground state, use the Hamiltonian H or H prime. It doesn't matter. Let's say we can use the only the H, including that constant piece. It's fine. Yeah, we can do this calculation. Then we should be able to work it out and obtain the double integral. Just to plug in both the definition of H and phi, right? You know both H and phi in terms of A and A diagram. You also know the fundamental computation relation between A and A diagram. You should be able to work on everything. So this becomes a double integral. This is omega k, meaning that the omega associated with k. Now, since I have H is my omega p. By definition, H is AP, diagram AP. Okay? Plus some constant piece proportional to the volume. And the point is this, now I want to compute this object, commute with some, for the commutator, as a commutator is other. The other is nothing but phi. Now I also plug in phi definition of phi in terms of A and A diagram, which is nothing but these two pieces. Okay? See? And just plug in the definition into. Then you can compute this commutator. Now you evaluate this commutator by using the quantization condition. Eventually, because of some direct function inside this integral, we reduce the double integral into a single integral. So basically set k equals to p. The direct function will set k equals to p. So you're get minus omega p eventually minus I p plus omega p higher eventually I p. This is a full vector human product. And use a dot. Okay, so this is the result out of that commutator. Now you can easily check. This is nothing but what is this? You observe it. This is almost the phi, except you have additional omega p and omega p, right? That omega p comes from, can be obtained from taking relative this vector phi. Okay? So this is nothing but minus I partial t. Yeah. So this equation is a very fundamental equation. There are many different understanding, interpretation of this equation, right? You see? We can read that this is nothing but a Heisenberg equation instead, okay? We can also try to take use of the knowledge we learned last year, because we know another definition for H is given by stress tensor, which is the current associated with symmetry, right? So you can view this H is, we also learned that H is nothing but the conserved charge associated with time translation. Last week, right? Right? Because it's T00 integral, space integral, right? T00, which is H, right? That's H. So H is the conserved charge associated with time translation. This equation clearly justifies that point. You see? If you take a commutator with H, you get an infinitesimal time translation. which is equivalent to take, say, a small parameter times with the t derivative, right? Right? A small, infinitesimal time translation, you view the delta hat in this way, right? Together with a small parameter. So this means the conservable charge H really generates time translation. Okay. So there are many different perspectives for the same equation. Right? Of course, the third one, you can view this equation as nothing but for any given two well-defined operators, you justify the commutator between them. You should be able to get a result. That's it. From the first principle, you should divide the commutators. So this is about the commutator for H and the other operator. This is the third meaning of this equation. Now, you did this stuff since for H. You can similarly did the same thing for the P, right? For energy, you can also do it for the momentum. We know P is about the T0I integral, right? Remember that? So Pi is the T0I x integral. This is the conserved charge for the spatial translation or space translation, okay? Space translation, that's P. So you can also treat the momentum P as the operator, just like this H. Do the similar thing for this analysis for the P. Okay? Now P is an operator, sometimes that's so waves and P is the real physical momentum of your system. So what if you do the same thing here, and there should be an operator definition for P, right? Last week we wrote down the classical field definition for P by doing a x integral for P naught I. For the I component for the third tensor, remember that as a conserved charge. Last week we got some formula that looks like momentum will be expressed as the x integral over some T naught I, which is basically I, in this case I partial I phi. Okay. So now we know both pi and this guy, right? You plug in the operator definition for pi and phi. Then you will be able to get the operator definition for P. So what is that? So you work it out. You get something like this. Get AP dagger, AP multiply P hat, okay? P hat is a vector. Inside this integral, you should think this is just some parameter, and it's not an operator. Only these two are operators, okay? But after this kind of integration, you should treat this capital P as the operator, right? Okay? Just plug in these two. Now, as the ground state energy check, you can also check a ground state P, right? You can do this calculation, right? So somebody asked, what do we observe? The thing we observe is the expectation value of this operator. In this case, it's just this one. So this is the vacuum expectation value of this P. Since this depends on the A dagger A, this easily check this is 0, right? Right? To justify our ground state for 0 momentum, Now, we mentioned, or somebody also asked, how to really understand. You claim that if you act the ground state by AP once, you will get a one particle state. How to justify it? Let's do that. So we just mentioned we act, for instance, any given P, some particular P, AP, act AP diagram on the ground state. The physical interpretation of that state is a one particle state. The one particle carries the momentum, like a plane wave, if you want to pictureize. But for instance, this is the one particle, not two particles, it's one particle. And it's not 0, it's 1. Now, how to justify, or how to, the interpretations depend on, to rely on the property, right? The property, how to justify it. Now, let's try to rewrite a little bit. Let's try to rewrite the combine with a normalization factor in omega p, 2 omega p squared. We just have this number. This is not an operator, it's a number. Okay, coming from normalization. I just rewrite this whole object with a single particle state, which carries the physical momentum p factor. So I can develop it this way. This is my definition. So to justify this is a single particle state, the one thing you can do is that you can really treat this as a new state. You can measure both the momentum and the energy for this state. Okay? That's something you can easily do. Because now you have well-defined energy operator, momentum operator. Now you have a concrete definition for which state you are going to consider. You just take the expectation value, right? So you can justify the momentum as well as energy for this state. So what do you get? What do you get? It's a piece of calculation that just do it for itself. What you get is the momentum is nothing but equal to square root. Sorry, energy is nothing but square root of momentum square plus m squared. Okay. This is what you get. You calculate both momentum and energy, you find this relation. Then you can get you're happy, right? Okay, this is really like a particle. That's why we call it the one particle state. Because I measured it. I measured what is the energy. I found this on-share condition. We know the on-share condition can describe the particle. Yeah, so this gives us confidence why this can be interpreted as a single particle with a particular momentum p, because we justified the on-share condition. Now, somebody also asked another some similar question. Now you're telling me just some very particular way. This kind of act will create a state that looks like a single particle. That's fine if there's evidence here. But what about the more familiar one? You see, what if now you're also telling me somehow phi itself is an operator, right? Now, what if I just use the phi itself to act on the vector? What do I get? How to interpret this guy? This looks more familiar one, right? Because everything is about trying to understand the quantum field theory. And the elementary object in quantum field theory is the field. Now, we also know the field has to be promoted to operators. Now this is a good operator, right? Now what about if I using this, since this is a good operator, now you should be able to interpret what happens if you act the operator on the ground state or vacuum. So what about that state? So which kind of interpretation of physics included in this state? This is the similar question. Yeah, we should calculate. Again, we should calculate. Everything should depend on the calculation. Right? We should work it out and see the properties. Then we can give the interpretation. So what is the result of this one? Just again, plug in the standard operator definition of phi hat. Just act on it, right? So we have two p's, A dagger and A dagger hat. Clearly, A dagger will not contribute, right? Because act on ground state to cure the ground state, you get 0. Now, now there is a remaining piece which contributes, which is the AP dagger. So after one step calculation, you can convince yourself. So the result out of this act, what you will get is something like this. We saw a structure coming from AP dagger acting on the ground state, which is what we just talked about. Okay, right? This is so-called a single particle state. Now we make use of this knowledge to write this result. Then this can be, the result can be related to the single particle state aerodynamic momentum. See, just write it in terms of P, because we have the definition for P here. Okay? Because we know there's a structure. I can write the result in terms of P. So we get this expression. So how to understand this expression, right? This expression suggests that that particular state is simply acted by some phi x is nothing but you have a bunch of different momentum single particle states, and then you put them together. You see? Is that clear? That's it, right? You put them together. So roughly speaking, this is some linear combination of different p. That's it. Right? This also can be understood, right? You know, usually we have a plane wave, but plane wave is so simple. It's even not localized object. In order to get more familiar localized object, you should linear combine or superposite all different momentum, right? Or different Fourier modes. We finally be able to get something looks like a local, something like a wave package, for instance, right? That's what it is. Yeah, that's what it is. You might unsatisfied by this kind of justification. You want to see more sharp evidence. There is one. If you are not satisfied by this argument, you can do something more. For instance, you can try to keep this state what you want to interpret by doing this state and overlap with another already known state. Okay? That kind of state. You take the overlap. Right? You can do this calculation. Okay? Do this calculation. If you do this calculation, because we already understood that this kind of state is some kind of quantum plane wave, right? Now, we should take use of something we already understood and try to explore the something we unknow or we don't know, right? That's the way, right? We want to understand this object. We don't know it yet, but it's fine. We just try to take it overlap with this familiar one. We already know that, right? And see the result. The result is given by, we just calculate it. Plug in the phi formula for phi. And this is nothing but the k. Okay, I just conjugate this k, cat state, right? K, then becomes a bra state. This is the AK. This A diagonal conjugate becomes AK. Okay. Now we also decompose it into a P integral with the overlapping factor. This is AP. Write everything explicitly. Yeah, this is all the operators now finally act on the ground state. Okay. So this is the thing I should plug in. So take use of the commutation relation to work this out. So what is this? This is the exponential I omega k t minus I. This is the final result. Is that clear? It's all about, you see, all about is AK. There is the AP diagram. Now, for the first term, AP killed the vacuum straight away. Okay. For the second term, combined with this one, there is the AP diagram. If you have AP diagram in the middle, you should take use of the commutators. Up to the commutators can be transformed into a different order. That different order again triggers. Okay. 0. So the only non-trivial left number is the commutator. If you employ commutator, you get a number. To get a number, you can extract from this state. In ground state, the overlap with itself is 1. You finally get some number, which is this one. So what is this? So in a compact form, this is nothing but the exponential I for k vector dot with x. So familiar? Sound familiar? Results? What is this? Yeah, this is the plane wave, right? This is the plane wave. So in quantum mechanics, you can have a plane wave, and you can have position eigenstate. You pick the overlap. We'll get something like this, right? You get something like this. So this strongly suggests this guy we already accept. For instance, this is the momentum. This is the single particle state with a fixed momentum, or roughly speaking, some kind of momentum eigenstate. Then this is to be treated as the closest counterpart for the position eigenstate of quantum mechanics, okay? Which is what? Which is the x. Okay? Remember that? In quantum mechanics, but this is not precise. I'm not saying this is the same, or this plays the same rule as the position eigenstate. This is not true. Okay? We will see very soon. But this is the closest interval. Okay? But there's a difference here. Okay? In quantum mechanics, we can safely say some state is sharply localized at x position, right? That's called the position. That's called the position eigenstate. Okay? It means this state is really some kind of very localized here, nowhere else. But this state is similar, but not the same. Okay? We will soon see that this is not a sharply localized position x, but it can represent localized state. Yeah, the local excited state, meaning that the particle, we excite a particle at x. And clear? Roughly speaking, it's more close to some real package chip localized state rather than a direct function. Okay? But this is a rough. This is not precise. We're justifying the carefully. Just a comment here. It's similar to the x state in quantum mechanics, but not the same. But to justify, to understand how this, what is the picture or what interpretation of such kind of state, this is enough, right? Because you work it out, you take the overlap with K state, because the exponential IKX. This already meaning that you are now obtained the some state which is similar to the X state in quantum mechanics. And yeah, so this is so what I want to clarify is this is the closest state to X state in quantum mechanics, and we interpret it as the excitation. Of course, it's a one particle excitation, right? The excitation at X. Right? I interpret, yeah, just understand this as I excited one particle at the X, that's fine. It's good enough. Yeah, that's fine. But what are the more detailed properties of such kind of state we will see in the remaining time? Yeah. Okay, that's one thing. Another thing, before we continue to discuss time property of this free field theory, another comment is we just worked out this property here. Again, let me go back a little bit. I don't want to forget. So we just arrived at some conclusion here, and we claim that this means the H can generate the time translation. Clear? But maybe for some of you or most of you, this is not manifest enough. To make it manifest, let's try to solve that differential equation. This is a differential equation. You see, there's a derivative with respect to t, right? Can any of you try to solve this differential equation? Tell me the answer. What is the answer for that differential equation? The answer is very simple. The solution for this differential equation, if you treat it as mathematically as a differential equation, you will always try to find a solution. The solution is actually very simple. And you can easily justify this is the solution by yourself. Yeah, you can justify this is the solution. See it? Just plug in. Someone tells you there is a solution. You should be able to plug in the solution to check whether it satisfies the equation. Right? Indeed. See? Plug in this right-hand side. Take the time derivative. This is nothing but the commutator with h. This is straightforward. You can justify it now. But basically, this means something interesting, right? This solution expressed in this form really means that h generates time translation. You see it? Because now, in this case here, my operator is located at t equals to 0. Okay? Time equals to 0. Okay? Now this operator now becomes the operator at time equals to t. You see? So this is about how to transform or how to drag the operator, transform the operator located at time equals to 0 to the operator at the time equals to t. So what is the object to does that transformation? In such kind of transformation. See? Okay? Just times the exponential IHT and together with exponential minus IHT. So this really means if you know H, you perform such kind of product or transformation, you should be able to get precisely the operator after time evolution, okay? Or at t time equals to t. And you can do the same thing for P, meaning X, okay? X. So compare this with the knowledge we learned last week. Last week, we expressed the transformation for the fields in an infinitesimal form. Remember that? Now, this is another version, but they are the same thing. This is the finite transformation. Last week, we learned the infinitesimal transformation. You should be also able to try to immediately justify if you treat this t is very small, you will get perfectly consistent what we learned last week. Okay, so just two things are just equal. Okay, if t is infinitesimal, for instance, you can do the this is exponential, right? You can approximate this to leading order to 1 plus IHT something. This is 1 times IHT, right? And you can throw away the higher order term, only keep the leading terms. You would just justify what we learned last week. So again, but these two things are physically the same. One is finite transformation, another is infinitesimal transformation. But in this particular form, we're talking about the time translation or time evolution, okay? Which is generated by this particular Hamiltonian operator, H. That's it. You can do the same thing for the P. Eventually, you can justify yourself for the entire space-time translation. One can always get a prime at x, which is 4 vector, expressed as I dx 0. It's a little bit schematic. Just including both time translation and space translation. We package everything into a 4 vector P. 4 vector P including H and that P. Okay? That P. Yeah, so, yeah. You can just justify yourself. Now, the question I would encourage you to do is what happens for Lorentz transformation? Yeah, I think this will be a good homework. Now, this is about the quantization of free fields. Do you have any questions? How much time do we have? We still have about 15 minutes, 17 minutes. Yeah, we can finish the remaining part and try the best. Yeah, this is all about the quantization of free fields. Yeah. So basically, with this amount of knowledge, you can work everything about the free fields. Everything, really everything. Okay? For any given operator, any given state, any physical observer. Okay? You can just compute it. Easy enough to work in everything. So, yeah, of course, this is the goal, but maybe before you aim to solve every problem about the free fields, let's come down to the errors to try to look at the minimum one. So everything we are now talking about is about some kind of single operator, right? A single operator or commutators, a single operator exploitation values, right? But in principle, you can touch many. For instance, this is about a single. This such kind of object is only about a single object. You see, single operator. Okay. But the point is, you can plug in many operators. It's okay. You can equally work with that. Sounds a little ambitious, but indeed. So this is the next topic. The minimal next easiest one will be the so-called, you have 2 phi operators, okay, inserted in the ground state, for instance. So this kind of objects, there are many different types, but this kind of objects are just called propagators. So what do we mean propagators? So the amplitude for a particle to propagate from say position y to another position x. If you want to characterize it mathematically, it will be something like this. This kind of object is called propagators, or roughly correlation function, 2-point function. There are 2 points. Of propagators. Right? And let's denote it something like D. Now you're asking me why you want to suddenly jump into talk about some kind of object. How do we know whether this object is physical enough to look into? Because we just justified some part of it, right? You see, we already prepared enough. You see, I just justified that this is really physically means you excite a particle, single particle, one particle at x, right? Then this immediately means since this is a real operator, you can treat this object as some state overlap with another state. You see, right? So we know well enough about this kind of state. It means just excite a particle at y. Okay, then you take an overlap with the other state excited at x. Okay.
I have a question. So why not phi at dagger?
Phi at dagger? No, phi is real. Phi is a real field. We don't yet touch complex fields. No such issue. Right? So this is physically is clear enough. Okay. You see? Now, since this is a conjugate, the overlap with that's a conjugate, a more straight interpretation will be you excite a particle one particle at the position y, then disappear or observed at x, right? Since this is the conjugate. This is the state about the conjugate of some excitation, okay? Which is roughly some annihilation or observed function, if you want to for this state. So you excite a state at y and then disappear at x. Then there is a probability or amplitude for this process, right? This quantity is about to measure such kind of amplitude. We learned in quantum mechanics, whenever you take one state overlap with another state, it has a meaning of amplitude, right? Now, again, this is not much new, right? So mathematically, we know we just claimed that we know enough tools to work out everything, something like including this. Just plug in the operator definition for both this y, phi x and phi y. Just plug it in, work it out using the commutation relations. Yes, you can do that. So after that, you can work it out. You will get. Now you ask me why don't you just denote the function, the final result as only x minus y. The reason is there's a translation invariance. Okay? There's a translation invariance for this kind of object. So you can always write down it as only a distance between x and y. Now, so this we defined this guy as said as the above object is about this propagator, and plug in this definition in terms of A and A dagger for both this and this guy. And finally work it out. Again, after 1 minute, you should be able to arrive the result. Looks like this. This is about the 4-vector inner product. Okay? So this is the result. Simple enough, right? But this is again, this is definitely the integral. But the integral itself is not trivial. Okay? You should try to work it out. How to do the integral with the very fine integral. But before that, let's observe some interesting thing. We already learned before. Both this part and this part are Lorentz invariant. Okay, this is perfectly justified that this object or this kind of 2-point function or propagator is Lorentz invariant. See, before you're doing anything, you should be able to observe that property. This is Lorentz invariant. Now, we try to calculate this object. I don't erase this important thing. So if we try to calculate this propagator, we can do 2 things. In general, it may be difficult to get a compact result, but you can do things case by case. For instance, we can first say, I can first say case 1, x and y are time-like. Right? But this is about the physical quantity associated with two different space-time points, x and y. X and y are Minkowski space-time points. Not only space or time, it's both and time. 2 points. Now, you can see case 1 will be time-like. Time-like. If x and y are time-like, and if the final object is Lorentz invariant, this means what? I can always choose a particular frame, right? Because the final quantity will be Lorentz invariant. Doesn't matter which frame I'm working, I should get the correct result. Is that clear? So I can choose the easiest frame I want. Okay. So in time-like case, the easiest frame I want is what? It should be only the time coordinate is differ from each other, but all other coordinates will be the same, right? Right? We learned it in the first course. This is the typical timeline, 2 points. So you can work in this particular setting. So indeed, in this case, you can work it out. The integral becomes a little simple, but again, not trivial. Okay? Yeah, I want to escape some details, but just show the step closest to the last. Something like this. It becomes some integral looks like this. Okay? Becomes integral something looks like this. Just work it out. Now, again, this integral is not trivial. Okay, so it's not trivial. If you plug it into Mathematica, it will give you some basic function. It's not trivial. But there is a reliable asymptotic for this integral, which is if t goes to infinity, this will be goes to asymptotic to exponential I mt. Yeah, this is the property of this one. The key impression, or if you need to remember, is that of course it's not zero, right? First of all, it's not zero, right? Whether this guy is zero or not, that's the first thing you should know. It's not zero, and how much it looks like. The point is, this is complicated, but when t goes to infinity, this will go to exponential minus I mt. So another case you can do is the xy are just space-like, right? Space-like. If these are space-like, we choose the opposite setting, which is the time is equal, but the space coordinate is different. The difference is r. You can use r vector. Now, again, in this case, you work out the propagator d x minus y, you will get the result. Something looks like this. This will be the result. Again, this integral is not trivial. The result will be a basic function. Okay, so I'm not going to carry into the details. This will be equal to blah blah blah. But the point is, this will not equal to zero. Okay, this will not equal to zero. This is the signal or justification back to the claim just said. These two guys are not completely equal. Because now I already justified, even at equal time, okay, two different space-like points, x and y. Such kind of two-point function is not zero, right? That's important. Because this two-point function, another interpretation is nothing but two single particle state overlap. See? In quantum mechanics, if you have x and x prime state, two position eigenstate, if you take different positions, the overlap will be completely zero, right? You see? That's in quantum mechanics. But it's not happening here. You do have a non-trivial overlap, even the two particles located at different space-like points. Okay? How can it possible? Why cannot? Yeah, I will give you interpretation soon. Right? First of all, this is the calculation result. Now you could challenge whether this is a reliable conclusion or not. It is a reliable conclusion. Why? Because this kind of overlap doesn't mean there should be an interaction between a space-like 2 points. It's just about the overlap. We already learned in quantum mechanics you can have an overlap. Even on the Earth, you are on the Moon. Okay? Because we know the superposition or quantum state there could be an entanglement. It's nothing fancy, okay? It's just about two-state overlap and different positions. That's very typical in the quantum world. So indeed, one of the key, explanation about why this can happen is coming from entanglement. So I mentioned also then this kind of object is not good enough to detect whether the operation at x and the operation at y can interact with each other. It's not good enough to do that because you see that even space like you get non-zero overlap. Then next question will be what will the more proper object you should study in order to detect whether x and y can interact. Okay, right? That looks more physical one. Yeah, indeed, there is such kind of quantity which is called commutator. So instead of looking at such a simple two-point function, we're now trying to detect something slightly complicated, which is the commutator. We already mentioned that such kind of commutator, we are not super unfamiliar with such kind of object. We already touched such kind of object in the commutation relation. For instance, the equal time line. Right? We actually worked it out already. But now let's do it in a more general way. In a sense, x, y now space-time coordinates, not only space, just four coordinates. Now, one thing is for sure true is the commutator, the output is always a number. It's not an operator, it's a number. If it's a number, then it doesn't matter you write it in this way or you take an expression back. That's just equal. Okay? Doesn't matter, it's a number. So let's do it this way. So why? You see, in this way, this looks more familiar with two-point function, right? Just about that I have two terms, a single term, right? That propagator, that particular propagator only has a single term, but now I have two terms. So this is the relation. Indeed, they are related. You can, for instance, you can write this in terms of dx minus y plus or minus dy minus x, for instance, right? But I'm not going to in that way. I really want to try to calculate this object, see whether this object has a real property as I want. In other words, just plug it in the operator definition of this object. Let's try to work it out, like what we did there. Yeah, I want to work it out, get a result, something like this. And indeed, this is nothing but two terms, two such kind of terms combined together. So the final result is this one, IP minus IP. So there are two terms. Yeah, so the way to deal with this guy is try to calculate it, and then if you get such kind of thing, then you see this is nothing but the dx minus y and the dy minus x. See, there are two terms you put together. Another way to deal with this right-hand side is just try to combine with the four-dimensional integral. Someone just asked me at the beginning, why don't you choose to expand everything in the four-dimensional space rather than three-dimensional space? Right? Yes, you can do that. Now, this is very useful to deal with in that way. I mean, employ the four-dimensional integral, momentum space integral to deal with such kind of structure. Okay? Yeah, so we have to stop.